With the nature of the electron now cleared up and all of its fundamental parameters now measured and determined, let's turn our focus to the remaining part of the atom. Right? What happens with it? What is this positive charge material that's making up the atom? Our current picture is this Thomson model for the atom. What I'd like now to do is to probe this model. Now, if you want to know what's going on inside of something, right, one of the best ways to do that is to hit it with a hammer and see what comes out. This is basically what's known as a classic scattering experiment. It's the best way to probe the internal structure of something. And basically, if you think about it, if you're interested, for instance, in particle physics, almost all of particle physics is scattering experiments, just like this, in order to probe the structure of things and the particles that make them up. So this really is going to be sort of a review of the first classic scattering or particle physics experiment. So let's go ahead and now let's take a look then at the experimental evidence for this. So this is a classic set of experiments that were carried out, of course, by Rutherford, very famous person. He was basically the main professor involved in this, and he published a very important paper. There was actually a whole series of papers on this subject in 1911, a very important theoretical paper where he made a whole series of predictions, and those predictions then were confirmed beautifully by two of his experimental colleagues. There was Geiger, famous for the Geiger counter, and actually there was also Marsden, who was a younger student actually at the time. Geiger was already a practicing physicist, and they published the experimental data which exquisitely confirmed Rutherford's calculations in 1913. And all three of them really had worked together and published a whole series of papers on this subject, on these types of experiments. So here's the basic idea of the experiment. We want, again, some kind of probe to the atom. And Rutherford had discovered a number of different kinds of radiation, and one of these made up one of the most perfect probes. He had found a certain radioactive material which acted as a source for a particular type of radiation he had discovered called alpha radiation. And so he has this source of his alpha radiation, which emits it out equally sort of in all directions. And this alpha radiation, these alpha particles, actually turn out to be nothing other than high speed, very quickly moving helium nuclei. So they actually are helium atoms, which are doubly ionized. It's just the nucleus of the helium atom. So the charge on these is plus, because it's just the nucleus. The atomic number of helium, Z, is our standard symbol for atomic number, times the amount of charge, and Z for helium, as we've been saying here, actually is just 2. Now, the way the experiment can be done then is you take that very powerful source of these very powerful rays and you put them in some kind of a lead box like so, right? Or use some lead columnating slits. The basic idea at the end of the day is by doing this, what you end up with then is a nice beam of these particles that are all traveling outward here in the same direction. Now, the next thing that I really want to emphasize is that this particular radioactive decay that they were using was very handy because of various conservation laws, it always emitted particles with the same amount of kinetic energy. And that amount was known, and it's about 5 million electron volts. Okay, so that is our probe that we're going to use to smash into these Thomson atoms to see what we can learn about their structure. Now, in order to have you need then a target, right? So this is the probe over here. We're going to need some kind of a target. The target that they used was gold. That's because you can form it into an extremely thin foil, which turns out to be very important. So let me sketch a thin foil here. Looks something like this, has a little bit of thickness to it, not too much. It's going to look something like so. So that's my thin gold foil. And just for reference for you all, gold is actually a fairly large atom, and it has a Z an atomic number actually of 79. Now, the way this experiment works is that because this foil, and I should say the thickness of the foil is known. Now, because the foil is so thin, I should say, it's made purposefully this way. It's thin enough so that, in fact, most of these particles actually pass directly through it without any deflection whatsoever. However, a good number of them, though, do interact with the gold atoms inside of this foil and end up deflecting, and they come out then at various angles theta, which you can then measure. So that's the basic setup or the procedure for the experiment. Now, the results that come out of it, or the, I should say, really the observations or the results that we find, are as follows. One of the first things, and it has very important consequences, is the first I should show you how they would display the data. So what you do then is you count, actually, how many particles scatter at each different angle, and you make a histogram out of this. Very much like the histogram that you would have for like your test scores in a class. So they counted the number scattered at each different angle theta, and then plotted that as a function of theta. They would, of course, just ignore the particles that didn't interact with anything, so we're not going to worry about theta equals 0. But then you look at the next small range of theta, and they typically would find some number are scattered into that first range above 0, and then they count how many are in the next range, and so forth. And if you're extremely patient and count thousands upon thousands of these, you can end up with a very nice finely defined histogram, which eventually will converge into some kind of a continuous curve, which you can measure, and has some angular dependence, and here maybe would be about an angle, say, of pi over 2. It's just a sketch. Now, when they look at these results, they find some very interesting things. The first thing has to do with the thickness. So when you change the thickness T, and this is why they were using a very thin foil, actually. When you change this thickness T, the first thing you notice is that the shape of the function that you get, the shape of this count function, stays the same. The only thing that changes, the only change, is that the number count that you get is directly proportional to T. So what that means is, if I took this foil, right, and I just doubled the thickness of it, I would get exactly the same angles of scattering. I would just have twice as much scattering. And this is extremely important as an observation for the following reason. For instance, let's just imagine I divided my foil here in half. Now, you might think that what would happen is this alpha particle would come in here, bounce off of one atom, go off in a different direction, hit another atom, go off in yet another direction, hit another one, and then finally emerge from the system. But we can very well rule out that type of multiple scattering process because of this observation. And the reason for this goes as follows. Notice, if I imagine splitting my foil in half, for example, or you can imagine doubling it. It's the same type of an idea, right? What we know is that if we just had the first half of this foil, I would get a certain set of counts, right? And that would correspond to all of the scattering from that first part of the foil. When I add the second part of the foil, it produces a pattern of scattering. But the pattern that it produces, because in the end I just end up doubling all the counts, it's producing exactly the same pattern. So it seems as though the same pattern. When I've got a piece of foil behind it, if I removed that piece of foil behind it, it would actually produce the same scattering, right, as the original foil. And that's important because that tells you then, because both pieces of this foil are producing exactly the same output, they must be experiencing essentially exactly the same input, right? They must both just be feeling things as though it were just the bare original incoming beam. As a counterexample, if a particle goes in and if a lot of particles scattered when they hit the first half, right, they'd scatter off in some set of directions. That would mean then the input directions to the second foil would be very different to the first foil, and it would certainly then not produce exactly the same pattern of scattering as the first foil. So that's a very key observation. We're not seeing, of course, there are always, a tiny fraction you might find, but we're not seeing in any significant numbers multiple scattering events. And that's extremely important because analyzing the multiple scattering gets extremely complicated because you basically have to think about like a crazy pinball machine here, right? But no, what this allows us to do is we can analyze each atom separately, right? Each atom is just scattering particles. Some completely miss my atom, some bump into it, but I don't have to worry about multiple scattering, so I can just analyze each atom separately and then add the results together, which is going to make our analysis, of course, much, much simpler. The next observation is that you can actually get a very detailed form for this functional form, and it follows a very interesting function that gives us ultimately a lot of key information. The function it follows is something like 1 over sine to the 4th power of theta over 2. And my third observation from this really isn't a major additional observation. It's just something I want you guys to keep in mind, is that we see significant scattering at a lot of angles, right? Significant scattering even at, and say, I don't know, I'll just pick an angle like theta equals pi over 4, and that just happens to be a favorite angle of mine. You'll see why in a moment, but that's because the tangent of that angle, happens to be 1. And this just happens to do with how I like to think about the results. So those are the observations and results. Next, I want to move on to thinking about the analysis.